Hi, welcome back to the breadboard. For this video we have another episode of Raspberry Pi with Windows 10. Everybody knows about this puppy, the new Raspberry Pi Model 2. It's been out for a little while now, so you're all getting to grips with it. But what not a lot of people know about is the Windows 10 that you can now get, Windows 10 for IoT, that will run in the Raspberry Pi. So I did a video just a few days ago on how to install it and get your first application up and running, and I showed you how also to use a Texas Instruments digital to analog converter, the DAC8734. That's all well and good, but not everybody has the wherewithal to start making breadboards and things like that. So what I thought I'd do for this one is something I think hopefully will be a lot more popular, and that is get Windows 10 to completely drive this thing. This is a PiFace 2 board from Element 14. You can get them all over the place. They're not so expensive, but they're a great way of interfacing relays and I/O to your Raspberry Pi with having a little bit of buffering. And because it's got these relays, you can put sort of 24 volts at up to about 5 amps on each one. You've got the green inputs here, which allow you to put some switches on there and ground the inputs to read them from your Raspberry Pi. They use a weak 100K pull-up resistors internally on the chip that's on here to do that. And then these outputs are all open collector drives from a ULN 2003 driver chip. So it can sync probably well in excess of a couple hundred milliamps. Channel 0 and 1 maybe not quite so much because they've got a relay here on each one, but nevertheless, if you disable the relays, then all of these orange connected ones, you can drive some of your external relays and various other things if you want, quite easily. Anyway, there was plenty of applications available for the PiFace Digital 2 under Linux, but I was unable to find anything really that would run under Windows 10. So I've written one. And what we've got is basically, and I'm going to show you this for real in a moment, but this is the user interface. And it's going to have, what it's got is these buttons. You can actually click them on the screen, or you can click them for real on the PiFace, and the program will read them in, and it will illuminate these lights that are across the top here. These LEDs that are over here, which are associated with the outputs, if you click any of those, you can toggle the output on or off, and the LEDs at the top here will illuminate as well as the ones here. The relays will also, if they're enabled to run, will click along with output 0 and 1 being pressed. You can also just simply click the relays and they will toggle on and off as well. And every time you do this on the screen, everything I'm talking about you can actually do on the screen. It will affect the real PiFace Digital 2 outputs and inputs. It's automatically reading the inputs every 200 milliseconds, so 5 times a second. It's reading all of the inputs as well as the output state, and it's updating these 16 LEDs along the top here, these pretend virtual LEDs. Let's say 5 times a second. So it will track, if you put some wires on here and you put some switches and you ground them, it'll track them and light these lights as long as they're not going too fast. I mean, you can tweak the program to make it scan a lot quicker. I just set it for 200 milliseconds for the sake of this demonstration. And that's pretty much it. It's effectively a Windows 10 version of the little UI app that there is available for Raspbian to drive the board here. And what I've done is, because the board uses a MCP23S17 SPI to 16 line output chip, I've written a separate library that will drive that. And so the main UI is the bit that really is aware of a PiFace Digital, but the underlying library that I've written is a separate class file. It's only aware of the 23S17 chip that's on the board there. So you could actually use that to drive pretty much any circuitry you like. And it's all going to be posted up on Element 14's website, on YouTube, and on my own website. So you can use it as much as you like, and no restrictions. But anyway, I thought I'd present this to you now and let you see what it does. So let's go have a look at the application working. So first things first, with the PiFace Digital 2 board, all you do is you plug it onto your Raspberry Pi Model 2 and just push it into place. I've already shown you how to load up the SD card with the Windows 10 for IoT for the Raspberry Pi, so I'm not going to go over that again. I'm going to assume that you've already got that configured and that you have Visual Studio configured to use the Raspberry Pi as its remote device and using an ARM. That's all you do to plug the PiFace Digital onto the Raspberry Pi. Now we're just going to connect up a network interface, well, actually we don't even need the keyboard, a wireless mouse adapter, because I've written the software to completely run with just the mouse, so you don't even need a keyboard. HDMI lead and power. So that's us booting up now. My screen will come up in a minute. I'll show you this in a moment as well, but the first things first, we'll bring the software up on my development computer, and I'll quickly show you what the pieces are so that you can have a look yourself when you download it. Okay, I'm not too sure how much of the Raspberry Pi operation you're going to be able to see here, but I've tried to position it in front of the screen so that when I start this thing up, you better see everything going on when I touch stuff on the screen. So we'll fire it up, the application, and see what we can see. So the only control I'm going to use on the actual Pi itself is a mouse, which is a Logitech wireless one that I have connected. So I'm going to go to the apps. I've already uploaded the application straight up to the Pi. I've deployed it on it, so I'm just going to go straight to it. I will show you on the screen in a moment exactly what that looks like, and I'm just going to run it from the web browser just to make things a little bit quicker. So I'm starting it now. So I put the splash screen on. There you go. There's the splash screen coming up. And in a moment it'll change just a little bit for the application. This is starting from a cold start, so it might take a few seconds. There we go. So it's got all the controls, and then the graphics got to load up. Alright, so this is the screen that we have that I've designed and programmed, and what we have on here, I'm just going to point to a few things, is the very first thing is up here. This is an exit control. So if you click this button, it will exit. We've got the image of the PiFace Digital 2 board as our main background for the application, and each of these buttons is actually active. You can click it and it will simulate the inputs being pulled to ground. You can also wire something directly to the inputs here, and it will also show on these LEDs, the virtual LEDs at the top, whether the state of the input is high or low. Now, because it's got weak pull-ups in the form of a 100K resistor up to +5, then with nothing connected and no switches pressed, the LEDs are in a high state, therefore, the inputs are in a high state, and therefore the LEDs are on. In the case of the digital outputs, which are these 8 here, you actually output a 1 to the controller chip. This is the chip here is the MCP23S17 from Microchip, and even though we're outputting a 1 to here, it actually goes through a ULN 2003, or in this case a ULN 2803 chip before it starts driving the load. So a 1 into here actually ends up with a low going out. So what I've done is, if the outputs are not set to a 1, to turn on the outputs, I've left the LEDs off up here, and if I output a 1 to the output port here, they will come on, even though the outputs are actually technically going to ground because it's an open collector drive. So you can click any one of these board level LEDs and it will toggle the output for you. You can also click the relays. I put a graphic over the top to show you the current state of the relays, and if you click it, it will actually toggle on and off, and the graphic will change to show you what the output is. And of course the relay outputs are over here. So you've got a common and normally closed and normally open. So if you wanted to drive something like a 24 volt motor or something, you can bring 24 volts into the common and then have the normally open go out to the motor, and then the other side of the motor back to the ground of the supply. You don't even have to bring it anywhere near the Raspberry Pi power supplies or anything like that. And by outputting a 1 on either channel 0 or 1 of the outputs, you will turn that relay. Relay 0 would turn this one on, and relay 1 would turn this one. So that's 0 and 1. And that's pretty much it. It's a very, very simple program. Well, it's quite a lengthy program because of all the extras I've thrown in, but it does a very simple job. It allows you to exercise this board without having to do any fancy programming. So just to show you exactly now what I mean, if I go over to switch 0 here, all right, I've got tooltips on everything as well. This is popping up to say click the button with the mouse to simulate S0 being pressed, so you can, or you can actually press the real switch. So if I press this, you'll see the light goes off because I've grounded it. And if I let go, it comes back on again. And I can do that for each of these. All right. Now you think, okay, that's great. I'm just doing software here, and I am. It's all being simulated there. But if I actually go to, and you can see me do this because I've got the Raspberry Pi sitting right down there. So if I can put an extra light on maybe to help with some illumination on it. Yep, there we go. I might turn it back off again in a moment just because it will wash out the screen and things like that. I don't know if you're going to be able to see this, but I'm going to try and see myself if I can. All right, so I'm actually moving these switches here so you can see them going on and off on the top of the screen. And if I do all of them, you know, they'll all go off, which is quite fine. And if I take a jumper, I just find one here to use, and I take it from the ground and I go to any one of these pins, you'll see that the respective lights will go off, showing you that it's actually reading it quite happily. See? Right, any one of them, all the green ones. So that's quite nice. Now the outputs here on the orange side, these ones, you know, you can't put things in easily to make them go on and off. So what I've done is I've made these LEDs active. So if I click the LED, it turns on, and the respective light on the PiFace Digital goes on and off as well. So if I click it again, if I get the mouse on it, if you look at the light on the screen, the red light's going on and off. The indicator above the LED is going on and off as I'm clicking it. But if you look at the actual PiFace Digital, you'll see the, I know you can't see too closely as to exactly which LED it is, but I assure you it is LED 7 that is going on and off. And I can actually go down the row and click them all on if I want to. 3, 2, 1. And you can hear now with this one the relay clicking in and out, and you can see the graphic turn on because the relay's been energized, and the graphic changing. On, off, on, and then 0, which is this one. I think I've got them the wrong way around on the wiring and the software, how to fix that. All right, so that's quite happily driving all the relays. Obviously you don't hear anything with the other ones, and as I said, you can simulate the inputs as well. And that's pretty much it. I know it doesn't seem like much, but I had to get there was no SPI library drivers for the MCP23S17, so I had to write some, and then obviously build a front end on it. What I wanted to do was make it look a little bit like the one that you can download right from website, either Element 14 or the PiFace website, to run under Linux. And I just wanted to make one that looks very nice and runs under Windows 10 for IoT. So that's pretty much what we have. So from an operation perspective, there's really nothing else to show you. I mean, there's a few enhancements that I might do later, and that would be to make these jumpers active so that you can click them and pretend you've taken them off or put them on, and have the program automatically adjust its address and things like that. But that's maybe for a future enhancement that I might do, or somebody else wants to pick up the banner and fly with it, then they can. You know, but being able to just go in here and turn these things on and off is really nice, and be able to connect real loads on here. And if you look at the software, as I say, I'm going to make it freely available. you can download it and have a look. You'll see exactly how I'm interfacing all of these buttons using XAML with C# and hooking it into the C# library in the background that talks to the SPI bus and everything else. So yeah, that's pretty much it. Real short. Actually, I think this might be one of the shortest videos I've ever done. I'm going to quickly show you the software now, just so that you can see or have an idea of where everything is. I'm not going to teach you how to upload it to the Pi again, because I've already done that. And I'm not going to show you how to set up Windows 10, because I've already done that as well. So this is going to be just simply looking at the software. Okay. Oh, the other thing too is, yeah, everything's got tooltips, and if you hover over this, it'll tell you quit the application. So you can actually nicely quit the application and go back to the standard desktop. This is the app manager, by the way, that I mentioned before, and what you can see here is in the installed apps, because I told it to deploy it, you can see that I've got all these different applications already installed. These first 5 are actually the default ones when you create the SD card. The bottom 2, the DAC 8734 tester and the PiFace Digital 2, are the 2 that I've created over the last couple of weeks. This, obviously, the one we're working on is the PiFace Digital 2. And all you got to do to run it is literally just select it from the menu and click start. It's already running on mine, of course, but you can see that right here. And if you want to end it remotely, then you can just click on the X, and it'll ask you to confirm that, and you can just stop it and it'll go back to the main screen again. So that's pretty much it for that. I'm not going to go through the web thing again, because we did that already too. What I am going to do is bring up the software. So like I said last time, I'm running Visual Studio Community Edition. This is the one that's freely available to everybody. They just have to download it and install it once they have Windows 10 up and running. A few other apps as well. Went over that in the last video, so again, not going to repeat everything. Alright, so as per usual, Windows 10 Universal Apps, the main screen is mainpage.xaml. Okay, so this is your basic general UI layout. You'll be able to have a look at this better yourself. The screen's a little bit small here. Let me see if I can improve things a little bit. Alright, so just bottom left corner, just pick fit to screen or fit all, and there it is. So what we've got is we've got some graphics items put on here. They're just they're toggle buttons, and I've given them a graphic and a little bit of software to toggle between the two. All of these lights on the top, they're just images as well, and I can change the source of the image file as depending whether they're ones or zeros. The buttons, again, the image of the buttons, they actually have toggle buttons superimposed on top of them that are transparent. Same with all the LEDs. I've just put transparent toggle buttons over the top for that as well. So all basic stuff, and I've just made it look prettier by giving it the Element 14 color scheme. Now on the right hand side here, what you'll see is the basically the 2 libraries. What we have is the MCP23S17 library, which is for driving the actual chip on the board, and then we've got the PiFace class here, which is the main app for driving the UI and making it look like a PiFace Digital. So if we go into the MCP23S17 and have a look at the code here, it's only the one file that really matters aside from references, and that is the MCP23S17.cs file. So at the top we've got a few using statements for the namespace we're using. We've got a namespace statement, we've got a class MCP23S17. Like previous videos, I've made this all static, so you don't even have to instantiate it, you just use it. Whole bunch of constant byte values. These are all the different registers. I just gleaned this from the data sheet and put in all of the registers with their offset values and things to make the coding easier. They're private because the user interface doesn't actually need to know about them. A few other constants for on and off and out and input and things like that. The base address of the chip, or the address of the chip, because you can change jumpers to put it on a different address. I've allowed for that in the software. And then we've got the base address where the minimum I2C address or SPI address is 40. And then if you are doing writing, then it is, sorry, if you're reading it's 41, and if you're writing it's 40 if you're using I2C. But you also, if you're using the hardware address lines inside the SPI chip, you still need to output the address to the chip to make sure that the right one is responding. Because you know, one of the things I've mentioned in the past with these chips is you can put up to 8 of them on one SPI bus with one chip select, and based on the A0 through A1 and A2, you can actually make him appear and behave a little bit like they're I2C devices, but of course they're not. So you output an address first onto the SPI bus once you've chip selected them. Then you output the register that you want to talk to, and then you output the data for that register. So we're using the SPI 0, we're using the chip select 0 line. That's basically baked into the PiFace Digital cards. Same initialization as we had before on the previous applications for the initialization of the SPI bus. We have 4 buffers this time. You've seen some code before where we had 2 buffers for the SPI bus, 3 in and 3 out, because there are 2 different ways of talking to this chip, one which requires 3 bytes and one which requires 4 bytes. And the Windows 10 for IoT write routine just takes the length of the byte array as its parameter. I can't just use one of them, so I've actually just created 2. They're only 4 bytes each, so it's no big deal, or 3 and 4 bytes. So that's nothing worth worrying about. We have the init for the MCP23S17, which basically says use hardware addressing and set up the default pin mode. So pin mode is where we talk about whether they're inputs and outputs. And I've set the default in the driver here to be all zeroed. So they're going to be all inputs, and they're all going to have weak pull-ups on them. But is it all of them? No, sorry. They're all inputs, and right now I've got half of them with pull-ups and half without. So you can change this to be whatever you like anyway, it doesn't matter. After the initialization, I've got a whole bunch of now routines, which is a whole bunch of utility routines effectively. This is write to an 8-bit register, and it just sets up the buffer and calls SPI write. The first byte going out is the address of the chip, which I mentioned it behaves like an I2C device, but it isn't. Second byte is the offset, and the third byte is the register value. Now remember, this is writing only 8 bytes, so one register, or half of the register, because they're all 16 really. Then we have a write 16, right? Write register 16. This takes basically the same format, except you're outputting 16 bytes instead of 8 bytes for data. So when you're outputting the I/O devices and reading the pins, you would use this one for outputting the 16 bits. Outside of that, the SPI write's exactly the same. It's just we're giving it the buffer with 4 bytes in it instead of 3 bytes. Set pin mode is a utility function that allows you to set each pin individually to an input or an output, and there's actually a uint16 variable at the top that will hold the current state in it, so that if you do want to change just one, you don't have to read any registers back. You just update the state and output the whole thing again. As I say, when you have a look at the code, I'm sure if you have questions, I'll be happy to answer them. And again, you write register, and you give it the register offset, and you give it the pin mode, which is that 16-bit register. And you can see here, pin mode is AND-ing the current pin mode, which the AND equals means use itself as well. And then you're ANDing in the state of the new pin. So if it's a 0, it's going to take it to 0. And if it's a 1, it'll take it up to a 1. It's because it's inverting this. So you're going to be putting it, ANDing the two together, and you'll get what you need. That's set pin mode. Then you've got a pull-up mode. Now, if you got these devices set to inputs on some of the pins, then you can also add a 100K pull-up resistor to that input internally to the chip, just to help you. So you just put a switch on it. That's what that does. Invert mode allows you to output a 1 to the chip, and the output will actually go to a 0. So you can actually invert the functionality of the output pins. And in some cases that would be handy. So for instance, right now, because the ULN2003 is on the output of the upper half of the register, you could do the invert and then say, well, if I output a 1, I want the output to be high or off. And if I output a 0, I want the output to follow it and go to 0 volts as well, which would mean turning on the transistors. You could simply change the invert mode here and still have the same logic as a 1 being, the same program, and it would just invert the output pins, and you wouldn't have to change anything else. Write pin allows you to write individual pins high and low. Read register, we've got a write pin, individual pins, and we've got a write word, which allows you to set the whole thing in one value as well. So it's handy if you want to set all the outputs to 0, for example. Read register 8 allows you to read just 8 bits from a register, and you specify the register you want to read from. Read pin allows you to read any one of the pins of the 16 pins, and you just give it the pin number, and it will return you a uint16, but basically it will give you the bit set or not, depending on what the value of the pin is that's on your input. Now this will also work for the output. If you wanted to read back and your code wasn't remembering what it had outputted already, you can actually read the output pins too, and it'll give you the state of what it's trying to do with it. I only return a 0 or a 1 depending on the pin state, irrespective of where the pin is. It's basically a Boolean. I just didn't want to make it more complicated with having a Boolean variable, so I just left it at that. And then the last thing here is just converts int takes the byte array, 2 bytes of the byte array, and converts it to an integer. So it returns a 16-bit integer unsigned. And all it does is takes the lower half ANDed with FF, and then takes the upper half of the data and ANDs it with, shift lefts it 8 places. And that's pretty much it. So it's really straightforward for that. The UI software, so that's all the driver software main page, and we'll look at the CS. What we have here is and then you got a few variables I brought up the on-off, so that from the MCP23S17, and I made it just a local variable, so I just have to say output equals on, output equals off to make it simple. Outside of that, I've got the binding and unload, so that when the page closes I could do some cleanup if I wanted to. I call a function from the main page startup called init_all, which does exactly what it says. It initializes all of the bits and pieces that we need initializing. We have an int timer, which currently is set to 200 milliseconds. And the function for that simply reads all 16 bits registers and calls a light LEDs, which will then iterate through the 16 LEDs and either turn them on or off depending on the state. This is the initialization. The first thing it does is initialize the SPI bus with a wait and within a wait statement in front of it. One of the things I found in the earlier versions of some of the software I was doing was that the SPI bus would not be initialized before my code started to try and do something with it, and I would get exceptions and things thrown. By doing it a wait, it'll actually wait for the SPI bus to complete its work before it continues the code. So now that I've done that here, I get no issues. And then I initialize the 23S17. I set the pin mode to half in, half out. I set the pull-up mode to half pull-ups, and the other ones I don't care. I set a 00 to the output to make sure all the outputs are off. And then I bind some event handlers for the switches. Some of these toggle switches I wanted to have it work such that if I was holding the mouse button down, so I was pressing the switch, the output would work as if I was doing it for real. And then when I let go of the mouse, I wanted it to come off. The problem is that if you've got a button, for instance, and you have a click event, when you hit click, it'll do that. But when you let go, you would have to fire a separate event and do the unclick. And I just wanted to be able to test the switches to say, is it pressed? And by having this handler here, you can actually do that. You can also have it respond to being pressed or not, and have it do other things as well versus the clicking. Anyway, you can look all that up just by Googling it and things. Light LEDs, all it does is it takes the 16-bit value that was gleaned from the MCP23S17, and all it does is takes each of the bits and tests it for being a 1 or a 0, and it sets up the appropriate image source for those virtual LEDs. So it either uses an image source for an on LED or an image source for an off LED, and that's all it does. You'll find plenty of examples of convoluted ways of changing the image for a graphical element in Windows 10 or in XAML. And you know, I looked at that and I thought that's way too much work, and all I did was I created the sample images on the screen and hid them. Basically I collapsed them, which means they don't show up, and then all I did was the image that I want to change, I just say image.source equals, and then pointed it to one of my collapsed ones, image.source, and I was immediately able to use those ones that were already rendered with very, very little code, which makes life a lot easier. And if you don't believe me, just Google changing the image source XAML C#, and you'll see exactly what I mean, and you'll see when you look at my code how simple this is. In fact, you can see it here. It's just image read on dot, I've got my image 7 output source. Depending on the state of this Boolean test, we'll either set its source to the image read on source or the image read off source. And these are two images that are on the UI, but they're just hidden, and they're not very big, so they don't take up a lot of space. After that, we've got a whole bunch of simple checked and unchecked event handlers. So these two are for the relay. If I click the relay, it outputs a pin to turn the output on, which obviously then turns the physical relay on. I change the graphic so that it shows you the state of the relay correctly on the graphic, and I turn the LED on so that the graphic for the LED also shows the correct state. Now obviously the first two LEDs, LED 0 and 1, behave that way with the relays. After that, for 2, 3, 4, 5, 6, 7, you'll see that there are no more, like here, there's 2. So all it does is writes the pin to an on state, which actually turns the graphic on. The button, the toggle button itself, takes care of changing its color, so you don't have to. Okay, that's pretty easy stuff. It's up to LED 0, unchecked events. I'm not going to go through every one because they're all pretty much exactly the same. This is the event handling for the switches. So I've got switch pointer released. And what I was trying to do here, it actually isn't working well enough because there are other event handlers that are overriding it. I was actually trying to change the border to go between red and black when I pressed the button and when I released it. So currently that bit's not working, but it's still there. It doesn't do any harm, and that's really it. That's the end of it. When I click the button exit, it calls this event handler the click, and I just do app.current.exit, and that exits the application. Right now I don't have any cleanup. I don't see that that's particularly an issue at the moment. But as you can see, there's a lot physically here, but really when you break it down into the individual pieces, it's very, very simple. So I'm not going to go into any more detail about the application than that. Take it, use it. You don't have to do any editing with it. You can just fire it up and use it on the Pi, and it will work quite happily for you. And if you like it, give me a like, and if you don't, well then don't. But either way, I hope you find it interesting and useful, and I'll be putting out some more soon. So that's it.